Hello everyone. Hello everyone. Welcome back. Today we are going to start this DP educational contest from the Atcoder platform. This is our first video uh, of the problem walkthrough from the problem of Atcoder platform. So I hope I will cover all the problems A to Z from this Atcoder DP contest. So this is the thing. They have 26 problems and which are really good to practice DP, and I will solve all of these and also post it on our channel, so stay tuned. I will leave this link in the comment description section as well. Don't forget to check it out. So that is it. And this is our question. There are n stones. This is mm, probably the first question you all will solve, or you would have solved related to the DP when you started to practice DP. So it goes like there are n stones numbered 1 to n. For each one less than or equal to I less than or equal to n, the height of stone I is hi. So there is a frog who is initially stone 1. He will repeat the following action some number of times to reach stone n. If the frog is currently on stone I, jump to stone I plus 1 or stone I plus 2. So here a cost of mod of hi minus hj is incurred, where j is the stone to land on. And then we have to find the minimum possible total cost incurred before the frog reaches stone n. So constraints are n is up to 10 to the power of 5 and heights are up to 10 to the power of 4. Input is like this. So let us consider this test case. First sample input 1. So it is like 10, 4 numbers, 10, 30, 40, 20, 30, 40, 20. Now this is height, suppose 10, this is 30, and this is 40, and this is 20. So what our frog wants to do is that from here he wants to reach here. So how is he gonna do it? So there are how many possible paths here? So from 1 he can go to 2, then he can go to 3, then he can go to 4. Otherwise from 1 he'll jump to 2 and then directly to the 4. Otherwise he'll jump to 3 and then 4, right? So are there any extra possible paths that he can take? 2, 3, 4, then 2 and 4, 3 and 4. So I think that is it. These are the three paths that he will take. So in the first path, this is the first path. Let us label it as second path and this as the third path. Here, from going from 1 to 2, it will incur the cost of 20. From 2 to 3, it will incur cost of 10. From 3 to 4, it will incur cost of 20. So with the alternative 1, he will have to give 50 units of cost to travel from stone 1 to n. Let's consider second alternative. So 1 to directly 3. So cost of 30 is incurred, and then 3 to 4. Again 3 to 4 means 20 is incurred. So finally again 50 cost is incurred. Now considering the third alternative, 1 to 2. So 1 to 2 cost incurred will be 20, and 2 to directly 4 cost incurred will be 10. So that will be 30. So 30 is the minimum cost. So this is the alternative that frog will take, right? So let us check if if answer is 30. Yes, answer is 30. In this test case, frog will directly jump from 1 to 2 with no height difference between the stones. So answer will be trivially 0. So And this is somewhat bigger test case. We will not discuss it, but idea is same. So what idea is that, suppose I am at suppose uh, to reach the ith stone, suppose frog wants to reach the ith stone. So from where he can reach the ith stone, he can reach from I minus 1th stone and I minus second stone. Okay, second or I minus first, you would have said this. This, so these are the only two choices from which the frog can jump to ith stone. So to reach nth stone, he wants to reach to n minus first stone or n minus second stone. Do you agree? Do you agree? So yes, and that is the whole idea of our solving the, that is the whole idea for our solution. Now how we will solve is that, suppose my function solve, my function solve of n, suppose solve of I, let us take it, solve of I returns how much is incurred from going from going to from going 1 to I. So which will be equal to, solve of I will be equal to minimum of minimum of solve of I minus 1 plus height absolute of, means mod of height difference of I minus height difference of I minus 1. Do you agree? And comma, see, this is the case when I am jumping from I minus first stone to the ith stone, and the second case would be I am jumping from I minus second stone to ith stone. Then here it will be hi minus hi minus 2. Okay, so this is the recursive call our function will make. This is the recursive call our function will make, and this is the pretty simple idea. So let us head directly towards the code. And where we will use dp here is that, suppose uh, 1 2 3 4 5 6, so 6 stones are there, let us suppose 6 stones are there. And uh, oh, finally my answer here, finally my answer will be solve of n, right? Because I want to reach the nth stone. And where we will use dp is that, suppose for 6 I will calculate solve of 4, right? According to this I will calculate solve of 4 here. Okay, so solve of 4 is calculated and returned to the solve of 6. So solve of 4 is calculated, but when I'll call solve of 5, so solve of 6 will call minimum of solve of 5 plus some value v1 comma solve of 4 plus some value v2. So so when this solve of 6 will call solve of 4, it will be calculated and returned to this minimum function. And when I'll call solve of 5 will again call solve of 4. Okay, solve of 5 will again call solve of 4. So I will end up computing solve of 4 two times. I will end up computing solve of 4 two times, which I don't want to calculate. That's why I will store store the index, number of index, and if it is solve function is calculated or not. Store, or you can use DP directly, dynamic programming. We just memorize the answers of each state. So that is what we will do. So let us take a look at the code itself. So this solve function is taking one argument as I, which is the index, then dp array to memoize, means memoize the answers, and vector v. So v is just the height array. I would have named it h as well, but anyways. So long dp of n. So I'm using zero based indexing basically. So filling the dp with some sentinel value minus 493 and calling solve of n minus 1 comma dp comma v. So what this solve function will do is that if I is 0 means stone is to be reached is the first stone, because I'm using zero based indexing, so we will return directly 0, right? We are already on that stone, so returning 0 is mandatory. And dp of I is not equal to minus 493, which is means not equal to this previously initialized value, means it is already calculated and stored. Where it will be stored, I'll tell you. So it is already being calculated, not being calculated, it is already calculated. So we will return directly dp of I, and if it is not calculated, it will surpass both of these criterias and come here. So long cost is equal to L long max. This is the max value that long integer can take. So if I is greater than 0, see, you have to check this condition before applying this, right? Solve of I minus 1. Okay, so otherwise if it was 0, then it will go solve of minus 1, and we haven't handled that case. Okay, so checking it is necessary. And solve of I minus 1 dp comma v absolute of v of I minus v of I minus 1. So we have discussed it here, right? So this is the first case, and the second case is that the frog jumps from I minus second stone to the ith stone. It is handled here, and again one check is required. If I is greater than 1, then only we will enter into the statement. And finally we will return cost, and we will memoize cost into the dp. So return dp of I is equal to cost, and that way finally we will get the answer. So yeah, it passed nicely, and hope you enjoyed solving the problem and listening to the solution as well. Thank you for watching the video. Consider liking the video and subscribing to our channel. Stay tuned for daily competitive programming discussions. Take care.